moisture moves downstream, it creates problem at each step. Conversion first is conversion of SO2 to SO3. Moisture in the process there has a direct negative effect on the efficiency and life of the vanadium pentoxide catalyst used in the converter of sulfuric acid plant. If moisture is not fully removed in the drying tower, it reaches the converter. Water reacts with SO3 present in the first pass up and onwards to form aerosols of H2SO4 inside the pores of the catalyst. H2, SO3 plus H2, H2SO mist. In the mechanism, water vapor competes with SO2 O2 for active sites on VTO5. Think of the catalyst surface like a limited number of parking spots. Normally, SO2 and O2 occupy these spots and react to form SO3. If water vapor molecules also arrive, they park in these spots too, blocking SO2 and SO2 from reacting. The direct competition reduces catalyst efficiency. Consequences: pore blockages, loss of active surface area, fall in conversion efficiency, condensations inside pores during cooling cycles causes cracking, crumbling, or some sintering of the catalyst pellets, shortens catalyst life drastically, catalyst replacement needed earlier, high cost. Increased pressure drop across catalyst beds, pores plugging lead to higher power consumption in main air blower. A2, if moisture is not fully removed in the drying tower, it will combine with SO3 downstream. Acid mist. The mist condenses in low temperature zones, cold spots, creating extremely corrosive dilute, and the corrosion is rapid. Acid dew point corrosion, fouling, and serious plant reliability issue. Where are the cold spots in sulfuric acid plants? Near duct walls, joints, vents, or areas where inadequate insulation. Gas-to-gas heat exchangers, low temperature surfaces where gas is cooled, interpass ducts if gas is not hot enough to keep water vapor above the dew point. High emissions. 1 minute, please. Yeah. When a moisture passes beyond the drying tower into the converter and absorption system, it reacts with SO3. Instead of gaseous SO3, which can be absorbed efficiently into strong acid, we now get microscopic droplets, aerosols of sulfuric acid, suspended in the gas stream. The absorption tower is designed for gas liquid absorption, not to capture mist. Acid droplets formed due to moisture are non-condensable aerosols and do not dissolve readily in sulfuric acid. Result, they bypass absorption and move up to the mist eliminator section, which can only capture a certain mist load. That was, what I have given in the slide number 6. For sulfur burning plant, it is 500 to 750. For metallurgical plant, it is 1000 to 1500 milligram per nm2. Extra mist formed due to residual moisture overloads damages mist eliminators. When mist load is too high, fine acid droplets escape with the tail gas and appears as a white plume at the stack. This is recorded as higher acid mist emission in stack monitoring. In a few cases, it may exceed environmental norms, leading to regulatory non-compliance. In practice, when the stack plume is visible, operators attack IP80 and FAT because these are final contact points before the stack. But the root cause is often upstream moisture slip, which feeds extra water into SO3 and produces more mist than the mist eliminator can handle. Yes. Yeah. The biggest irony. In many sulfuric plant, moisture control is given in lesser importance as compared to other process parameters like converter temperature, SO2 SO3 balance, absorption tower, power consumption ratio, steam generation ratio, etc. The reasons are more operational and human factor related than technical. Here's why. Misconception of simplicity. The drying tower is often seen as a simple absorption column with strong acid circulation. Operators assume as long as acid is circulating, moisture must be removed. This leads to a less focus on distributor conditions, circulation rates, or acid concentration and temperature. Invisible effects in short term. The effects like catalyst plant poisoning, acid dew point, corrosion, mist elimination, etc., appear weeks or months later, making the link to poor drying less obvious. Priority basis. Converter temperature and absorption efficiency are visible and regulated KPIs linked to SO2 emissions. Moisture control isn't usually a direct regulatory parameter, so it gets lower priority. The biggest already can do. Yeah. Organizational knowledge gap. Newer operators may not fully understand the critical link between moisture and catalyst life. Training often emphasizes conversion and temperature control, but now not how to moisture ruins catalyst performance. Hence, the drying tower is not treated as critical equipment, but rather as a utility. Lack of the online monitoring. Many plants don't have online viewpoint or humidity or analyzer before the converter. This makes moisture control seems less required, so it is neglected in day-to-day operation. Not measured regularly leads to out of sight, then ultimately it is out of mind. It is normal human psychology. Not measured regularly means no real-time data for moisture